Hello everyone, thank you for listening to my presentation. My name is Kai Liu, I'm from University of Florida. Today I will talk about my proposed project called Low Complexity Impulse-OFDM Design and Analysis for Medical Body Area Network Services. In my presentation, we will first talk about the Medical Body Area Network. Then I will focus on the design challenges for designing communication system for medical band services. Then I will propose the low complexity Impulse-OFDM schemes. In the final of my presentation, I will evaluate our proposed scheme. So, what is the medical band? The medical band is the one application of body area network. The usage of the body area network includes the body sensor network, wearable audios, and the mobile device controls, and the medical applications. Body area network focuses on the on-body sensor or in-body sensor communications, or between the communication between device to the on-body sensor networks. The medical body area network services include vital patient data and the health monitoring, the hospital wellness connections, and the fitness monitoring. Nowadays, the patients in the hospitals are connected a lot of sensors, and these sensors are connected with the control center with cables. These cables make the patient really uncomfortable. The wireless communication technique can free the patient from these cables and also can help the doctors to monitor the patient dynamically and automatically. The background of the medical bands is proposed by the GE Healthcare. GE Healthcare also petitioned the US FCC to allow the use of the frequency band of the 2.36 to 2.4 GHz band for the medical body area network services as a secondary use. IEEE also set a task group to draft a physical layer standard in such a band, which complies with the FCC medical band laws. The target of the medical body area network services is for the low power consumption of communications. And for some medical applications like the ultrasound imaging systems, that they require high data rate. Other systems like the healthcare monitoring, vital sign monitoring, they require low data rate but very high reliability. So the targeted applications need the communication system to support scalable data rate. The draft of the IEEE standard also includes the communication distance, the network throughput, latency, and network setup time. By comparing with the existing communication techniques like the Zigbee, Bluetooth, Wi-Fi, and ultra-wideband, medical body area network are focused on the low power consumption part. But the medical body area network are really ambitious. It needs to support low data rate to very high data rate. So the requirement on the low power and the scalable data rate requirement need us to design advanced communication techniques to support such demand. So in this project, we're utilizing the current physical layer techniques used in the 2.4 GHz band, like the front-end, antenna, filter, and amplifier. We also combine the baseband processing of the OFDM to the low complexity transceivers of the impulse radio ultra-wideband to reduce the cost and the power consumption of whole system, and also using the frequency domain processing approaches in OFDM to improve spectrum efficiency and reliability. These two figures show the conventional OFDM transmitter and the receivers. So in upper figure, it shows the transmitter of the OFDM. The transmitter utilizes the RFFT to modulate the information in the predefined subcarriers, then using DAC to change the digital signal to the analog domain. In the receiver side, the ADC will sample the analog signal to the digital domain, and the FFT perform FFT transform the signal to the frequency domain, and then extract the information carried in the subcarriers. Then we can obtain the binary data. This figure shows the amplitude of the frequency domain. Every point shows subcarriers. This is the phase information of each subcarriers. And this is the generated OFDM symbols. So in the OFDM receiver side, this is the magnitude of received spectrums, and this is phase information received. So the receiver extracts the phase information and demodulates the information carried in the phase. We also conduct a Monte Carlo simulation to evaluate the beta error rate and the average phase errors of OFDM on different modulation schemes. From the BER result, we know that the BPSK modulation achieves the best performance, but with very low data rate. The high-order communication scheme, high-order modulation schemes achieve very poor beta error rate. Actually, we also set a channel standard for the hospital band to help us to evaluate our proposed scheme. So in our project, we focused on the scenario S6, that is body surface to external communications, that is the channel 4, as shown in these figures. These two figures shows the channel impulse response of the scenario S6 of the CM4 channel model, with different communication directions, like the body direction to the communication channels. This is 4 kind of degrees. By applying the same 4 channels in the OFDM systems, the BER performance is really poor. Because the OFDM system used in our project is really simple and don't contain the channel modulation schemes, so the poor beta error rate is understandable. The most advantage of the OFDM scheme is its high spectrum efficiency and high data rate support. But the disadvantage of the OFDM is its very high compressed receiver architecture. It needs high-speed DAC to generate the waveform, and also needs high-speed ADC to sample it back to the digital domain. So with the development of the digital processing unit like the DSP, FPGA, and ASIC techniques, the digital resources is sufficient to processing the IFT and the IFT used in the OFDM. But the high-speed DAC and ADC becomes the bottleneck of the whole systems, because the high-speed DAC and ADC consumes a lot of power and really high cost. So this is also the reason that OFDM scheme is only used in very high compressed communication systems like the 4G LTE. Another communication system is called Impulse radio ultra-wideband. The advantages of the Impulse radio ultra-wideband is it can use a very low compressed transceiver to support high data rate. But it also has some drawbacks like low spectrum efficiency, and it cannot use the matched filter to reduce the noise because it's very sharp plus used. So in our project, we utilize the low complexity transceiver architecture of the Impulse radio ultra-wideband, and perform frequency processing in the OFDM, and combine these things together and propose a balanced performance in complexity and communication data rate. We still use the sharp plus as the impulse radios as the transmit signal, but different from the IR-UWB, over generated sharp process have different position patterns, and we record these position patterns and record this spectrum as the matching template. So in the receiver side, we actually perform spectrum matching between the recorded patterns to the received signals. So if these two patterns are really similar, then we can demodulate the information. So this is a transmitter and the receiver of our proposed Impulse-OFDM. From the first figure, it shows that we don't need to use the IFFT in the transmitters. The only module that we use is to modulate the time series plus in different position patterns, and then using plus instead of the high power DAC to generate the plus. The plus generator can be implemented by SDR circuit or direct using the digital jet to represent the sharp plus. So the overall complexity of the transmitter can be significantly reduced. In the receiver side, we sample the received plus to the digital domain. Some research results have been shown that using monobit or very low resolution ADC can sample the impulse radio ultra-wideband signal and can achieve very good performance. So we don't need to use the very high power, high compressed ADC. We just need to use a very simple sampler to sample the signal to the digital domain. Then in the receiver side, we like the OFDM system, we still perform FFT. Then we perform the spectrum matching between the per-defined spectrum patterns. Then we demodulate the informations, obtain the binary data. This is over the spectrum matching result. In this example, we detected the pattern 3. That means we detected the symbols like 0010. To evaluate the performance of our proposed Impulse-OFDM designs, we also conducted the Monte Carlo simulations between the conventional OFDM and the Impulse-OFDM when using the ideal plus, and the Impulse-OFDM when using the Gaussian plus. The red line shows the conventional OFDM. So from this figure shows that in the high SNR side, conventional OFDM cannot achieve very good performance. But using the our proposed Impulse-OFDM approach, like the red line shows, when SNR is larger than 9 dB, the BR is equal to 0. When using the Gaussian process, the performance is slightly degraded. But we still can achieve very high performance in the high SNR side. We also conducted the image transmission experiment to evaluate the performance. So the left figure shows the initial images. When SNR is equal to 8 dBs, the obtained OFDM results, the BR of the OFDM is really higher than our proposed Impulse-OFDM approach. And there are a lot of noisy points in these figures. When SNR is increased to 15 dB, our proposed Impulse-OFDM achieves 0 BR, which is very good. Now let's show the demo in MATLAB. There are two functions. The first function performs the impulse radio OFDM modulation. The second function performs the conventional OFDM, and will transmit the initial figures into these two figures. This figure shows the result of using the conventional OFDM. So there are a lot of noisy points in these figures. This figure shows our proposed approach. This figure is really clean. And it is how we achieved by using our proposed Impulse-OFDM system. That's all. Thank you. Thank you for your attention.